for having me participate today. So the subject is the flood damage mitigation works of the Miami Conservancy District, Ohio, been in operation since 1922. So topics I want to cover: a brief professional history, rain-generated superfloods, and flood damage mitigation, and the example is Miami Conservancy District. So first of all, my early professional years, Newcastle, Australia. There's a map of Australia. There's Newcastle, 100 miles north of Sydney. There's a Google image looking down at the port city, and the scale there, a half a mile. And that's the old University of Newcastle, where I attended from 1962 to 1966. And there are a total of 199 degrees granted for all the graduates who completed 1966. It was a small school. We show there Hunter District Water Board. So I did summer internships as a trainee civil engineer at Hunter District Water Board from 1963 through 1966. I was a member of construction crews that was building sewers, water supply, treatment plants, pumping stations. I gained huge respect for workers who do hard physical work. And I also learned that engineers must not waste any workers' time. So I served as a construction engineer from November 66 to August 67, and that was with Hunter District Water Board. It's now known as Hunter Water. And I had two major jobs. One was lowering the spillway at Watershed Dam for enhanced dam safety. And the second one was earthworks for expansion of the Tomago potable water treatment plant. Graduate study was at Stanford University Civil Engineering, picked up a master's in '68 and my doctorate in 1970. I joined the University of Washington Civil Engineering faculty in 1970 as an assistant professor, went through the ranks, was professor in '79, and I gained a PE license in February of 1980, which I considered important as an educator. Became Professor Emeritus in June of 2010. So I want to talk about, first of all, rain-generated riverine superfloods and why superfloods are important. They differ substantially from lesser floods. They're infrequent. They exceeds about 10 to the minus 2, so they're very infrequent. They cause the greatest societal disruption and damage. So what essential information do you need to handle a superflood? You need to know the domain. You need to know the meteorological context and storm sequence. You need to know inundation details, and you need complete flood hydrograph at multiple locations. So as to give you an example of this, I'm picking on the Great Flood of the Upper Mississippi River from May to September of 1993. So here we have from the USGS report, there we have the Upper Mississippi River and May to September of '93, and they're the three major portions that are involved. And you get a sense now of the on the Missouri River, and here you're looking at river flooding on July 30, '93 in the vicinity of Cedar City and Jefferson City Metropolitan Airport. Total disruption to society. And another USGS report, they did an amazing job reporting this. So we look at the flood domain, and that's the area of flooding streams. It's a very extensive area. And there's St. Louis. Now we look at something else. We want to look at the precipitation in the Upper Mississippi. So we're looking at the meteorology. And we're looking at the dominant weather patterns of the United States from June through July of '93. So we're concerned with the storm sequence, and the jet stream defined where things happen to be. So we have convergence zone recurrent thunderstorm systems. You have up here warm, moist, unstable flow from the Gulf. You have unseasonably cool, dry air up at the north, and it's the collision that gave rise to the massive storms. The resulting flooding extent near St. Louis. So first of all, I'll show you no flooding in 1991, and you're just looking at the riverine pattern. If you look at the image from August 1993, both are NASA images, you're looking in there and you see massive inundated areas there with a scale across there of 65 kilometers. If you go closer with higher resolution in St. Louis area there, the reddish pinkish ones are where you have infrastructure and you see the very large inundated area. If we take a look, again, a USGS part of report, the Mississippi River at St. Louis from May to August of 93. So you're looking at time window there, May to August. You're looking at the discharge in cubic feet per second. And every dot there is a river flow measurement. It was measured every day. So the peak discharge was 1,080,000 cubic feet per second. But what is really telling, here's the National Weather Service's flood discharge level, and we're looking at multi-months of inundation. So the multi-month duration results from sequence of storms, upper basin hydrology, operation of reservoirs, and failure of levees in the system. So how should we design for flood damage mitigation? This has been known for a long time. And I think the best book that's ever been written on floods was by Hoyt and Langbein in 1955. And I just point out it's essential reading. But here we have some important part from this. Floods and ongoing national flood risk from pages 9 to 11 from their book. Meteorological and hydrologic conditions combine to produce superfloods of unprecedented magnitude. We have every reason to believe that in most rivers, past floods may not be an accurate measure of ultimate flood potentialities. It is this superflood with which we are always most concerned. If we look at flood damage mitigation, and we have a comment here, floods are an act of God. Flood damages result from acts of men. That's from House Document 465 of the 89th Congress, and it was the document, A Unified National Program for Managing Flood Losses, and that was in August of '66. I come now to the Miami Conservancy District, and our first lead in here, and it's an example of flood protection works at the river basin scale to address life cycle societal resilience against rain-caused superfloods. So how did I learn about the Miami Conservancy District? Well, it's by serendipity. It was by subtle guidance by Professor Ray Lindsley, my doctoral advisor, precious mentor, and friend. Ray asked me in 1976 to write a paper on water resource systems planning 1776 to 1976 for the bicentennial. He suggested that I might find the works of the Miami Conservancy District informative. So I have the next slide to show that. Thus began my 46 years historical interest in this work and the work of Arthur E. Morgan, and I revisit it frequently for inspiration. So here we have March of '79 ASCE, Journal of the Water Resources Planning and Management Division, and we were restricted to 50 characters for title, Water Resource Systems Planning in USA, 76 to 1976. So from the introduction, the key part down in here, the systems philosophy was articulated at least as early as 1915. I could not find an earlier version. And it was by Arthur E. Morgan, Chief Engineer of the Miami Conservancy District. So what is systems engineering? The systems approach requires formal identification of objectives, criteria by which alternative solutions may be evaluated, and constraints. These activities can be difficult to perform. If improperly identified objectives are examined, the resulting system will fail to respond to the real problem that initiated the planning effort. The generation of alternatives depends upon technological, human, and resource limitations. Alternative solutions to a problem are a function of time and place. So a solution that worked 150 years ago may not be valid now. Implementation of the preferred alternative is one of the most difficult planning activities when conflicts necessitate modification to the preferred alternative. So this gives the term satisficing or satisfactory solutions proposed by future Nobel laureate Herbert A. Simon in 1947, rather than optimal solutions result. Good system plans will be robust to changing demands or uses. Good system plans will be robust to changing demands or uses. So let's look at U.S. flood damage mitigation and dam safety legislation, because everything we do is in this boundary. There's been extensive federal legislation over a century, and it's summarized in Table C1 and C2 from a book, Dam and Levee Safety and Community Resilience, A Vision for Future Practice, published by the National Research Council in 2012. I was a member of that committee. There is the cover of the book, and I'll provide access information to you in another message. So first of all, we look at the principal laws and policies shaping dam safety governance. And the first was the 1917 Flood Control Act. It was the first major flood legislation, and it dealt primarily with levees on the Mississippi and Sacramento rivers. This followed in 1928, expanded the part to include control mechanisms, and the policy extended to include floodways, spillways, and channels, provided the foundation for dam safety legislation. We go now to the principal laws and policies shaping levee safety. So we have the 1917 Flood Control Act. And there, the US population was 103 million people. We go to 1936, declared flood control a federal interest and vested authority in the Corps of Engineers. The levees along the main stem of the Mississippi became federal. This was for both navigation and integrated solutions. We come to 1955, and they directed the U.S. Army Corps of Engineers to provide emergency repair or rehab of federally authorized flood control works. The U.S. population was 166 million then. We're now double that population, and floodplains, sadly, have been a bit occupied. So I come now to the book, the Miami Conservancy District. It was written by Arthur Morgan, and it was written in 1951. And it was a rare 25 years post-project effectiveness assessment of the works of the Miami Conservancy District and its excellent social, political, economic flood engineering. So the flood protection works for the district have been in place since 1922. They were built following disastrous flooding in March of 1913 in the Dayton, Ohio region. Some 360 bodies were recovered, hundreds disappeared. An estimated 20,000 homes were destroyed in Ohio, mainly in the Great Miami River Valley. Hamilton and Dayton suffered the greatest damage. Approximately 10 square miles of Dayton were inundated. And the solution to this is an excellent example of integrated flood damage disaster prevention and systems and life cycle engineering. The Morgan Engineering Company, headed by Arthur Morgan, was asked on May 5, 1913, to examine the entire problem. From a systems engineering approach, the charge of the local citizens' flood prevention committee was a rare single objective. The valley has suffered a calamity that must not be allowed to occur again. Find a way out. So what and where are the floodworks of the Miami Conservancy District? Well, we look at a map of Connors. There we have Dayton. Pull up a bigger map here. There we have the Ohio River. There we have Dayton. There we have Hamilton. And there we have the Great Miami River. So the Miami Conservancy District was established in 1914 as a way to address this problem. It encompasses the entire catchment, 4,000 square miles, and it overlays 15 counties. And it provides, even for today, a model for governance and public infrastructure funding that provides ongoing financing for operations and maintenance and replacement. We look at the Great Miami River Watershed. The green area there is the catchment area, and that's the district. The catchment area is the district, and there you see the 15 counties. So if we look at a map showing you what's on a sense of scale, there's Hamilton, and I go up there to Topeka, and that distance is 50 miles. So the integrated river basin solution included 3 dams on major tributaries that are critical components. There are Englewood Dam there, Huffman Dam, and Germantown Dam. The pioneering work on reconstructing flood-producing rain and assessing future possible major storms is absolutely amazing. It involved an extensive scientific and engineering hydrometeorological investigation and international data gathering and assessment. This is document in Technical Reports, Part 5, published in 1917. Many of you have seen this map in a textbook on hydrology and probably wondered why it's there. It's one of the most important that's ever been done. So it's the reconstructed rainfall. It's the storm of March 23 to 27, 1913. And there you're looking at 10-inch contours, 254 millimeters. There you're looking at 8-inch contours, 2 and 3 millimeters. The rain fell on saturated ground and approximately 90% became runoff. And this is the origin of the work of probable maximum precipitation. In a sense now, showing the rise and fall of the Miami River at Dayton and Hamilton. Hamilton being downstream has a higher flow rate. The gauge height in feet, going from 0 to 40 feet, and before the flood, it was about 4 feet. The thing that really is noticeable here is a 5-day sharp up and down, but the rapid rise, much of it occurred at night, and there was no real flood warning. So what dominated the hydrograph shape? Well, the storm orientation aligned with the catchment, and the channel system is a highly efficient drainage concentrator. So here we go, the Great Miami Watershed, and we have very efficient second-order feeder channels, one on the Mad River and one on the Stillwater River. And we have third-order main channel with multiple inputs between Dayton to Hamilton. Here, the solution that's in place now, and it's been there since 1922, there are 5 major dry dams. There are channel hydraulic improvements, so each little black mark in there is a height that's 55 miles of levees and channel improvements. But the significant part, notice there are gaps between the levees, it's open floodplain. So I just want to show you some examples of levees and channel armoring. And the first up is in the Dayton region. It comes into play here. And we're looking at Google image and a scale of 1 mile there. So there you have an engineered channel and levee. You notice it's curved and doesn't look natural at all. And over here is Huffman Dam on the Mad River. And I've highlighted there the Wright-Patterson Air Force Base. And the significance of this, the site was selected by Orville Wright and Arthur Morgan in 1917 as the United States was getting ready for involvement in World War I. Orville Wright chose it on the basis of the wind patterns for flight, and Arthur Morgan helped decide that based on where water would be backed up from Huffman Dam. We look now at a double-scale map, Dayton major levees and channel widening. So there you're looking at engineered channels and levees. And there's a portion where you have no levees. We come now to looking at levee and hydraulically efficient channel liner near Dayton. They're the original materials, and I photographed them on a visit to the region in May of 1984. The first up is a levee top, and down here is an innovative flexible revetment to retard bank undercutting. It's a very clever solution for a very difficult problem. And here we have laying the blocks for flexible revetment. You see 2 men holding that. That would be thought of as a 2-man rock in landscaping work. The person sitting is threading steel cables through them, so they're literally held together. The modern day equivalent is what you see here, lifted in with a crane and a geotextile. Construction of revetment in 1920. First of all, you have best practices for concrete placement, and there you have the flexible revetment. Now, how effective was this? Here's a photograph in Morgan's 1951 book, the same location taken about 1942, held up remarkably well for at least 20 years. I have a photo showing you bridge, all sorts of things, a bit of deposition along there. That could get scoured out in a very heavy flood. There we have a sense of the scale. There's a rental car, you know, the height of that. There you have there the recreational portion there, the pathways along the levees, they're very robust levees. And now we come to the significance of the first use of dry dams in the US. They're effectively large detention reservoirs. So how did dry dams become part of the system-wide flood damage mitigation design? This resulted from application of conclusive engineering analysis. This was Morgan's description of what I call systems engineering, as explained on pages 284 to 286 of his book, The Miami Conservancy District. On page 284, a general principle was adopted for approaching the solutions of the engineering problems of the Miami flood control, which I have termed conclusive engineering analysis. The principle, in essence, is that to whatever extent the importance of the work justifies, every possibility for solution of the problem, whether promising or not, should be explored with effort to become aware of unrealized and unexpected ways of approach. And that each such possibility be explored to a point where, in comparison with other methods of solution, it either is proved to be inferior or finally emerges as the best possible solution. From page 285, in the search for solutions to the Miami River flood problem, the different ways of approach were assigned to different engineers or groups of engineers. This is important. At that time, I had little or no expectation of finding a solution by means of dams and retarding basins. One reason why the possibilities of dams and retarding basins in the district project were not sooner appreciated was at that time few topographic maps of the possible basin sites had been published, a data-poor situation. It would not have been supposed that here in populous Ohio would exist some of the finest and least obstructed sites in the country. While the process of conclusive engineering analysis had its most spectacular results in developing the possibility of retarding basins, it was applied in practice throughout the job and with many interesting results. One of the most distinct of these was the development of the hydraulic jump design for dissipating energy at the dam outlets. This was an early use of hydraulic jumps. We come up a little further. Years later, so this is in the 1951 book, years later, while spending an evening with Thomas Edison, who you all know, at his home, I asked him this point-blank question: do you have any general method for solving a problem? He said he did, and outlined substantially the process I've described, but with greater elaboration. In some cases, he said he would have as many as 40 possible answers to a problem before he would begin the process of comparison and elimination. Rarely, he said, did his final solution have any noticeable similarity to my first inspiration or hunch. That is a powerful message to every young engineer. So was there existing proof of the effectiveness of the use of retarding basins for flood damage mitigation? The Pinay Dam on the Loire River in France. Waters that were retained for short duration behind the Pinay Dam deposited rich sediments that enhanced the productivity of the inundated land. And here we have a photograph from a book. Arthur Morgan provided the photo. The dam was constructed in 1711. And you get a sense there, the retarding basin had an open width of 19.7 meters. So it held water back, but still let a lot down the channel. And here we have, it's 45,000 square miles, a fifth of the area of France for the Loire catchment, and Pinay is located just about there. So we go to a Google image and I have a scale of a mile. There's Pinay, but there's something in here. Down at Villarest, there's now a multi-purpose dam, does hydro, water supply, and flood mitigation. It opened on 11 September 1982 and made Pinay Dam redundant. If we look now at a fairly detailed scale, that is the approximate location of where the Pinay retarding basin, which operated from 1711 to 1984. That was a remarkable piece of engineering. So I want to go now and discuss features of the 5 dry dams and their locations, because there's important engineering about each one of these. So first of all, a map from 1925, the inundation extent when dams were operated for the design flood, the map prepared in 1925. So the most upstream was Lockington, and you notice the area that's inundated is not large. We go down there to Taylorsville, we go across there to the Mad River Dam, we come up here to Englewood, the largest, and we come over here to Germantown. So you're looking at that, and that water is going to drain out fairly quickly. Google Earth image of the region just to see what you would see looking from Lockington down to Hamilton, and you can't pick up a lot of detail from that distance. All 5 dams were constructed by the hydraulic fill method using materials dredged upriver. And this was done before the development by Carl von Tazagi and others of soil mechanics, now called geotechnical engineering. So from Morgan's book, we look at hydraulic fill construction. And you notice in there's some pipelines. They're hydraulic lines that carry water and sediment. And you see a pool level in there as well. So you start off there, you have to dry place materials so that you have somewhere for water to run. Notice there's a cutoff or core trench put in there to stop underground seepage. And then you notice the portion up there as the dam has come up, it's rolled frequently. So it's the best practice of what we do even today in an earth dam. So the hydraulic fill process, again, looking in here, there's a dredge pipe that's coming along, spreading water. There's the core pool, and there you have the fine settlements settle in the core pool. If we look at the cross-section for Germantown Dam in the district putting in here, first of all, the sheet piling put in there. So they've really understood the importance of stopping subsurface movement. That's the region that's the fine impervious material. That's really becoming your tight barrier. Coarse materials grading to fine. So think about coarse and getting finer as you get in towards there. And something very interesting here, take a look at the spillway crest. And you notice this is the emergency spillway. The upper part lacks an impervious core, and that's been added in dam safety upgrades starting in 1999 at Englewood Dam. So it's life cycle stuff. So effectively cutoffs have been put along on top of the original impervious. So I want to go now to Google images of the dry dam location. And I want to start first of all at Lockington. It's on Laramie Creek, which is a major upper tributary to the Great Miami River. And we go down here and we're looking at a 1/10 of a mile scale. And there's the dam spanning the valley. But roughly in the middle, you have a control device to restrict outflow. Think of a culvert that you're designing and you have a rough idea. It has an emergency spillway. And there you see the direction of flow. And in this particular image, there's no restriction on flow. The river is flowing naturally. You get a sense of the outlet works. You're looking at Lockington Dam, completed outlet structure, and the workers are standing at the hydraulic jump formation structure that was put in place there. Get a sense of the regional's farmland that's there. It's very attractive country. 0.1 of a mile scale here. I go downstream now to Taylorsville Dam on the Great Miami River. And we look at here, 1/10 of a mile scale. And we see the dam, earth dam, that's spanning the valley. But what's interesting, you have controlled outflow there, and it's across to one side, and you have an emergency spillway. Here you have water flowing in this image, which is from September of 2019. It's flowing in completely natural mode, and you see farmland behind there that would be inundated during storage. This is a photo from May of 1984. Here you're seeing unconstrained river flow, but the structure is designed to restrict the outflow as water built up. So it's a hydrodynamic design. Notice the curvature there for efficiency, and you have to have dam removal required after flood. You have the crest of the emergency OG spillway. So looking down on this, and at double scale, what I showed previously, you have some woody debris, and that's in September of 2019. And there you have natural flow coming down through the system. But you have a hydrodynamic control wall to prevent outflow crossover chokings. You have that wall there to make sure that they don't choke the control device. So you have bedrock. They took advantage of every bit of rock they could. Forced concrete structure to contain the hydraulic jump produced by flow of the emergency spillway. So you're looking at here, and that's that part. But what is interesting, the hydraulic jump forming domain, you're looking in there, those two bars there, that's where the jump is used to dissipate energy. And from May of '84, photo I took, Great Miami River, unregulated flow, and you're looking there at the wing walls, and you're looking at bedrock. Come now to Germantown Dam, and this one is a very interesting piece of engineering. So the Google image, 1/10 of a mile, and there you have the dam across the valley. There you have controlled outflow, and there you have an emergency spillway, which is removed from the dam itself using the local topography. So there you see the pattern of the unconstrained Twin Creek flow. We go to a scale a bit more expanded. So you have the emergency open channel spillway. And there you see the place where water would flow and bypass the dam quite safely. Here's a photo from May of '84. It's an inexpensive and efficient emergency spillway bypass channel. The engineers who did this were incredibly talented. So it's just soil-covered bedrock at this point, and it only gets to be used if the dam gets up to the level of that. And the water flow path is thus. So here's a slide courtesy of Dave Rogers from Missouri University of Science and Technology. And the comment he has on this one, the Miami Conservancy project witnessed the transition from beasts of burden to mechanized transport for common earth moving. The upper slide shows work on the spillway for Germantown Dam in early May 1920 using Fresno scrapers and hopper dumping wagons. The lower image shows shovels loading dump trucks on the Great Miami River levees in Troy, Ohio. So there you see a pretty impressive shovel, and there you see what was state of the art for a dump truck at that point. So I want to go back and have a look at some features here again. We look at here a 1/10 of a mile scale. The structure there is to control the outflow to restrict it to a maximum rate. But there you see some dentated work across there for energy dissipation. So the other thing we have to pay attention to is the stable bedrock all around there. So any bypass that goes around there is completely, the dam itself is protected from any of that. Here we see a photograph from May of '84 of unrestricted flow coming through the two conduits. And there you see a couple of folks standing by the safety fence. The safety fence is very high for very good reason. If anyone falls in, they die. So we go to Huffman Dam on the Mad River. And every dam has a sign like this. So Huffman, one of 5 dams built by the Miami Conservancy District for flood control in the Miami Valley, was completed in 1922. Height of 73 feet, length of 3,300 feet, and at the width at the base is 380 feet. But what is very important is that granite sign. And on that is the words, the dams of the Miami Conservancy District are for flood prevention purposes. The use for foul development or for storage would be a menace to the cities below. That's keeping in mind life cycle and trying to get to make sure people don't forget. So here we have Google image of the Huffman Dam, 3,300 feet across. And a question, what are those? So the Mad River in this particular image is showing no restriction at that point. In this is a dam safety issue. There were 48 relief wells to control any possible underseepage, reduce uplift forces, and they were installed between 1979 and '83, and I visited it in '84. Here's where the consulting board is hugely important, coming up with best practices. The dam safety, all 5 dams now have relief wells. So let's take a look at the hydrodynamic design of the outlet works. So in the upstream side, There's the controlled release. If the water gets up above the top portion of the hole there, it's restricted. There you have the emergency spillway. But something else that's very interesting is the time history of Portland cement concrete chemistry. So you're seeing some things there that will be needing replacement or whatever at some time. Downstream side, divided outlet flow to make sure you don't get any choking. Come down and look here again at the outflow controls are very similar design to Taylorsville Dam, and the unconstrained flow is coming through in this particular mode. Go now to the last of the dams, the Englewood Dam on Stillwater River. So here we go, the region and 1/10 of a mile, and there's the dam. There's a lake and picnic area. The Stillwater River is flowing in this image in an unconstrained way. Again, you have a sign there. The height is 125 feet, 4,700 feet. The width at the base is almost 800 feet. This is the biggest of the dams. The granite sign is under that snow at this point. We have 1/10 of a mile. The Englewood, quote, dry dam or retarding basin. It's a National Historic Civil Engineering landmark designated in 1972. The dry side, there's no permanent flood. Look in a bit more detail, and there we have 0.89 of a mile across. There's the emergency spillway, and there are the controlled outlet works to restrict the flow. And that's a 2014 Google image. If I go now to a 2016 Google image and increase the scale, so it's double the scale I was showing, and we look at relief wells to control under seepage and reduce uplift forces, and those white dots you can see along there, each dot is a well. Down the bottom is controlled seepage release structures that are also being put in place. It has a low-cost emergency spillway, and when I first saw this, I thought this was amazing. So this photo is in May of 1984. It's existing rock with shallow soil cover. There's the overflow path. It goes down and curves around there, and you notice there's a ditch for it to happen. In the construction, notice there's outflow armoring that's put in place. There's the top of the dam. There's the clearance between the bridge and the OG spillway. So we're looking in here now, and there's the engineered OG spillway. It's 100 feet across, and that's the path the water would go down. If I look now from the control works, I'm looking upstream. There's the Stillwater River, there's the recreational lake, and there's the weir. And you notice the flow can come into two parts there. Those vertical bars you see are for stop logs to stop flow down so work can be done. You look at the outflow, it's a gravel bed Stillwater River, great uncertainty on sediment transport prediction. Engineered wing walls, similar design to all of them, and there you have the flow coming out. And at the side, I'm showing you roughly the path that water would be coming from the emergency spillway, completely bypassing the structure at no risk. So take a look at the Englewood Dam outlook. That has 1919 on the date of it. So the discharge output in 1929, and the group there inspecting are the board of consultants in there. So the water is flowing down the other outlet, and that one is fairly dry. Again, a courtesy slide by David Rogers. And during flood event in January of 1930, you're seeing there the discharge. The critical element of the 5 dams / detention basins were intended to function without human intervention. There you see again a maximum outflow rate going through the structure. So a few details on the construction because it's very important. Rock excavation for outlet conduits at Englewood Dam. And we look in here, and there's the Stillwater River. There's the trench excavated in bedrock. And there are 2 conduits. The cross-section is horseshoe-shaped, each 13 feet wide and 10.5 feet high. You got a sense of those from the earlier photo. But something very important, here's the conduits ready for the dam to be built over them. And it had horizontal seepage retarding barriers put in there to stop piping and damage along there. That's the part where you have the highest heads that could be flowing. There you have, these are the section through, this is the section through Germantown Dam outlet conduits, and Englewood are very, very similar to Germantown in the part there. If you look now, the pool of the hydraulic fill at Englewood Dam. So the hydraulic fill is flowing that way. It's not flowing at this point, but there you have coarse materials, there you have fine materials, and that pool needs to be drained off for the rolling to be done. So how does a dry dam work? So let's look at flood peak reduction, and the example here, many of you have seen this in a textbook also, without explaining why it's there. So its inflow for a flood like that of March 1913 is actually the design flood. And there you see the outflow. So there you see a peak of 85,000 cubic feet per second without the dam, and there you see a fairly uniformly restricted with a max of about 11,000 cubic feet per second with the dam. So there's no human intervention needed. And whenever the inflow rate exceeds the outflow rate, the hatched area there shows you that's where floodwater is stored. Whenever the outflow rate exceeds the inflow rate, then you're having release. So you have a filling period of that window, and you have a total of 28 days, and it's emptied. So let's look at the emptying times for the dam peak stain, for the peak design flood. So the ones off channel are the ones that matter. Englewood is 28 days, Huffman is 5, and Germantown is 8. So you're occupying land for a relatively short period of time and achieving an enormous amount without having land set aside permanently. Look now at the annual flood peak flow rate at Dayton, Ohio from 1895 to 2021. So here we have the peak discharges at the Great Miami River at Dayton. And we're looking at 1895, 2020, but the last one's 2021. Thousands of cubic feet per second. So the official plan, the works are designed to be able to handle 110,000 cubic feet per second at Dayton. The 1913 flood, with the flood protection works in place, would give you 94,000 CFS. Without the works, they'd be 250,000 CFS. The maximum flood since it's been in place is 60,900 CFS. So been remarkably effective. But the 1913 flood was the flood of record. The facilities, levees, dams, and hydraulic efficient channels were designed for the 1913 flood peak plus 40% additional runoff. Keep in mind, they had very short record to be sorting this out. There has not been a flooding problem since implementation. There is ongoing updating for dam and levee safety and repair and replacement of aged concrete. As an example of this, we're looking at Huffman Dam and concrete replacement in 2020 by Synesis Construction. So they've set up to maintain and keep this stuff working properly. There's an annual report every year, and it has the latest details of all life cycle system updates. They're included in the annual report. The white-haired gentleman is Kurt Reinhardt, who'd been chief engineer for many years. He just retired. So notice here, annual report and the report of the chief engineer, the Miami Conservancy district, and there are 3 other districts reporting as well. So why is this work exceptional and inspiring? It's the first integrated river basin solution in the US. It had total community involvement. It was the first US dams and levees engineering solution. And much modern engineering was done here first. A lot of what you guys do in hydraulic engineering was done there first. The work was done under the exceptional leadership of Arthur Morgan without federal funding. It was path-setting, innovative, and inspires. It includes fail-safe and safe fail features worthy of study. The 1970 Flood Act required levees-only solution to flooding. The 28 Flood Act included dams and spillways. Much was learned from this work. The project timeline. The flooding and deaths occurred in March of 1913. The design started in 1915. The works were completed in 1922. A typical modern project is 30 to 40 years. You get MCD detailed reports at several places there, their publications. You have something, there's a wonderful Flood of Memories book showing images for 1913 and the corresponding image today. And you also have things about the watershed. I'll make sure you have access to these parts. So I have some summary observations from personal experience and studying excellent water resource engineering works. Make sure there's a captain of the ship. The captain has full knowledge of the operation and delegates. Arthur Morgan was an exceptional captain of the ship. He had detailed understanding of every aspect of the flood protection scheme. He and colleagues hired the best engineers they could find to do this innovative work. The establishment with the full engagement of the community of the Conservancy district and its governing structure guaranteed there would be no loss of institutional memory and ensured life cycle engineering and societal engagement. The district is overseen by its chief engineer, board of directors, and board of world-class consultants, the latter meeting in Dayton for 5-year inspection tours. So how do we replicate the spirit of Morgan and his approach? In addition to a ship's captain, seek out several wise colleagues 30 plus years older, including retired professionals, to serve as mentors. Engineering mistakes are repeated about every 30 years. Invite colleagues to help you think of all ways that your design or system could possibly fail and the societal consequences. Whenever I hear the term, we're anticipating the worst but hoping for the best, hope is never a strategy. So we come to questions at this point, but first of all, I have to say a major thanks to my wife of 52 years, Sylvia, who insists I refresh my field hydrologic observation skills. And there we are in 2017. So I guess we'll fire away now for questions.
Thank you. Thank you very much, Steve. Anybody have any questions? I didn't see anything in the chat, but feel free to turn on your camera if you want and address questions to Steve.
I gave him a lot to chew on.
That's for sure.
So Steve, this is Jeff Rice, and I do have one question. In just about the last slide there, you talked about, I think something to the effect of engineering mistakes happen every 30 years. Can you say some more about that? Where does that number come from?
Yeah,
if that's the case, I've only made 2 or 3 mistakes in my life, but I find that hard to believe. So,
one of my mentors, the late Professor Colin Brown, distinguished member of ASCE, he got me thinking about that many years ago, and he was citing examples that could happen. And the real rub is a lot of stuff is not documented very well. So engineers on the job know something about it, and they sort of remember it. And if they're and you look at a typical professional lifetime, it's on the order of 30 or so years, some are around longer. And that information goes out the door. And that's the real trouble. So if you look at, for example, the metro failure we had several years ago, that was an absolutely unforgivable mistake. And if you'd had the early engineers involved at that point, that would never have happened. So some of you probably have forgotten that one already. But the reality is we have to make sure there's continuity of information. And the Miami Conservancy District is one of the rare organizations that make sure there's ongoing remembrance of what's happening. So the number 30 may be a little tricky, much like inventions are an average of about the 35th iteration of the original idea. And you look at a can of WD-40, and that can, it's literally formula number 40 is the one you're using today. So keep in mind, you need to be getting hold of folk who have remembered something. And I can cite some other examples where I found out by going back and finding a colleague who was involved in something and pointed out that there'd been a diversion in a catchment that was not recorded anywhere, and I couldn't get the damn catchment balance right.
thank you.
Excellent. Unfortunately, Steve, I don't think we're going to have time for the Oroville Dam, and I was looking forward to that.
Let me just put up a very brief portion of it.
Sure.
Whoop. And the reason I want to put this up, I think it's very, very important that people know about it.
Just before you start, Steve, whoever wants to stick around for a few more minutes, feel free. We're just going to keep the presentation going a bit after 1 p.m.
So thank you those who've been here with us. But here's an example of the importance of loss of institutional memory. It's the failure of the spillway and severe damage from flow over the emergency spillway at Oroville Dam, the most important reservoir in the California State Water Project in February of 2017. The January 2018 independent team forensic report highlights the failure to consider full life cycle design maintenance. There was no oversight of the system of comparable robustness to that for the Miami Conservancy District. And here I have the cover of the report, the independent forensic team report, and it shows you photos of some of the devastation. The first one shows you the failure of the Chute spillway, and the second one shows you the damage of the emergency spillway. And that was published in January of 2015. So everybody who does anything in water resources should read this report. It has a wealth of information, and I think I should leave it at that.
Okay. Indeed, Jeff. Well, again, thank you very much, Steve, for the amazing information and the presentation you gave. I have a couple of quick questions if nobody has any of them. So obviously you have vast experience on dam design and iteration. So are you in generally satisfied with the progress that has been made, I guess excluding the Oroville Dam, in the past 50, 70, 100 years on this field?
I think there's been enormous progress. And for example, the best dam safety program probably in the world is with the Bureau of Reclamation. And that followed a major dam failure back in, I think, 1976. And that was in Idaho at the Dayton Dam. So they did a heads up check very carefully, and they've got some of the most thorough stuff around at this point there. But one of the problems we have, there's a shortage of folk who are actually doing designs these days of major structures. But what we're really about is how you keep things going. And when a lot of dams were put in place, the needs of society were different. So if you look locally at the dams on the Skagit, then when they were first put in there was a small population, there were abundant fish elsewhere and so forth. So it's a totally different game, but the caliber of what is able to be done is fine, but the real issue comes down to maintenance and operation and replacement.
Yeah, the lifetimes span over decades. So yeah, you're definitely going to have societal changes and differences in needs as well. And that's kind of a prelude to my next question, Steve. At some point, I think it was about the Huffman Dam, you said that there was a plaque that mentioned that it was for flood prevention, and it was not for, I think, power generation and one more potential use. So I have a physics background, and I feel I always, I have a note in my heart when I see that kinetic energy of rivers and streams being lost. Do you have a sense of how much would it cost, compare, let's say, to the cost of the dam to maybe retrofit power generation in dams already there?
The beauty of the structures that are in place. Notice I said if the design conditions came on Huffman Dam, I think you're looking at 5 days with water stored behind. So you're making a very minimal taking away from the river to help modulate the floods. The bulk of the time, the river is flowing as if it's natural, the great bulk of the time, and that's the case for almost everything. The Englewood Dam would have water held for as long as 28 days. This is if you had a huge flood come again. People wanting to do hydro, it has challenges. Anytime you store water, you're interfering with the river. There's no free lunch. We haven't repealed the second law of thermodynamics.
Mm-hmm.
So you look at the history of how people did energy. There were literally water wheels on rivers. Then as people could build storage and do other things, and then you come with the whole issue of electricity generation, AC or DC, then you have a huge change that come into place there. So then we went away from water wheels to other things, supplementing with electricity. So there's no real answer to that. But the reality is, if someone wanted to plug those three dams on the tributaries in the Miami Valley, they'd be making permanent floods. And this is a major issue. You're taking land out, it's a major cost. So it's a single purpose solution, and it served the region very, very well for a long time. So anytime you have water stored, and there's a very, very interesting point made on the Columbia River, the issue about the dams on the Columbia being wonderful for flood damage mitigation. An attorney for the Yakima Nation also raised the question, what about the permanent floods that have taken out other parts of land? So you gain something, but you lose a lot of other things as well.
Absolutely. Yes, it would definitely need to be on a case-by-case basis. Well, thank you very much again, Steve, for the presentation, and thank you all for attending another meeting of the chapter. And Michelle, I don't think we have any news on this at this point. So
before you both go, thank you, Michelle, Dimitri, and everybody who's working to make these meetings a valuable continuing education process. I've attended quite a few of them by the web mode, and they've been wonderfully instructive. And I'm just very, very pleased to see the caliber of young colleagues who are practicing the profession these days. You guys are just great.
Thank you. Thank you very much, Steve.
Thank you. Just one quick note, everyone. Our next meeting is the 18th of August. So be on the lookout for our next meeting invite. But that's the only thing I have. Thank you both. Looks like there's a hand up too.
Perfect. Have a nice evening, everyone.
Hey, Dimitri, it looks like there's a hand up.
Oh, sorry. Yes. Yeah, Robert. Yes, go ahead.
Hi, yeah, my name is Robert Schomp. I work for Kleinschmidt. I just wanted to sneak this in at the end. I didn't want to intrude. Thanks, Steve, for the wonderful presentation. Next week on Friday, July 29th, we're actually going to tour the River Mill hydroelectric project operated by Portland General Electric in Estacada, Oregon. I set up an event through the ASCE Younger Member Forum in Portland to have a technical tour of the dam. So we've got a few slots still left open for anyone who's interested. I'm not sure how many people are in Seattle for EWRI, but I know I call in from Portland, Oregon for these wonderful presentations. So yeah, if you're interested in going on the technical tour next week at 12 p.m. to 4 p.m. on Friday, July 29th, all you got to do is Google the ASCE YMF Portland, and we have the event and registration links on the website.
Thank you very much, Robert.
Yeah, thank you.
Perfect. I don't see.
I guess we're done.
Yes, we are done. Have a great weekend as well, everyone. Take care.
Thank you so much for everything.